Section: Introduction. In this section, we discuss large language models, which are trained on a wide variety of text types. For instance, a foundational model might learn to write news articles, create web content from the 1990s, and engage in passionate discussions about fictional characters. While these diverse capabilities are intriguing, they can be challenging for average users to manage. The introduction of ChatGPT and similar models has made the chat approach popular, allowing users to interact with models that act like helpful assistants or chatbots. We also have instruct-tuned models, which are designed to respond to direct questions or commands, such as asking for interesting places to visit in San Francisco or outlining a proof for a mathematical conjecture. These models can be enhanced with features like system prompts, which guide how to interpret instructions, or tool use, where the model can access external data or computations to improve its responses. Following this approach, we present Hermes 3, a series of instruct and tool using models that excel in reasoning and creativity. Among open-weight models, Hermes 3 stands out for its performance on various public benchmarks. Our training involved a wide range of synthetic reasoning tasks and expressive applications, ensuring that the model adheres closely to system and instruction prompts. This sets Hermes apart from many commercial models, which may decline requests based on ethical considerations. We recognize that large language models have limited direct agency. Instead, it is the systems we create with them that provide any real influence. We believe that safeguards should be implemented at the system level rather than on the models themselves, as overly restrictive measures can stifle creative thinking. For Hermes, we do not impose restrictions on potential ideas. In terms of model overview, Hermes 3 consists of highly steerable instruct and chat-tuned models fine-tuned from Llama 3 with varying sizes. These models are designed to align with the perspectives outlined in their system prompts and respond accurately to user requests. Their sensitivity to these prompts is especially notable in the largest version, where a blank prompt may not trigger the expected helpful assistant behavior. Hermes 3 excels in maintaining coherent, contextually relevant conversations, making it ideal for interactive scenarios, particularly with the extensive context window provided by Llama 3. Beyond the standard assistant role, Hermes 3 offers advanced capabilities that go beyond typical language tasks. Drawing inspiration from evaluations like MT Bench, the model shows significant improvements in judgment and reward modeling, allowing it to assess the quality of generated text with a nuanced understanding. This can facilitate effective fine-tuning and iterative improvements. Hermes 3 also includes several features to enhance multi-step problem-solving, such as structured output using XML tags, scratchpads for intermediate processing, internal monologues for clear decision-making, and visual communication through diagrams. We trained the model on reasoning tasks using specific tokens for various functions, which collectively enhance its ability to tackle complex tasks and communicate effectively. For instance, in coding tasks, Hermes 3 can generate complex code snippets in multiple programming languages and provide detailed explanations. It demonstrates a solid grasp of coding paradigms, making it a valuable asset for software development. Additionally, Hermes 3's capabilities can be expanded through tool use and retrieval augmented generation, allowing it to plan, incorporate external data, and utilize tools transparently. This makes Hermes 3 an excellent choice for tasks requiring agency and interpretability. Section Summary. In this section, we introduce Hermes 3, a series of highly steerable instruct and chat-tuned models that excel in maintaining coherent multi-turn conversations and adapting to diverse personas. We highlight its advanced capabilities, including structured output, transparent decision-making, and effective problem-solving, which enhance its performance in complex tasks such as coding and interactive scenarios. Section: Data Mixture. In this section, we describe our data mixture for Hermes 3, which includes a wide variety of high-quality instruction data carefully selected and generated to cover many domains and use cases. We began constructing this dataset in March 2024 and completed it in August 2024, following a strict selection process to ensure the data's quality and relevance. Our curation method involved using both existing datasets and generating domain-specific data. We assessed existing sources based on their coherence, educational value, and reliability, which significantly contributed to the general instructions category, making up a large part of its 236 million tokens. To address the limitations of general instructions, which often include random questions from users, we added domain-specific data covering areas like coding, mathematics, role-playing, and more. We used generation techniques inspired by Evil Instruct, even though this required more computational resources, to ensure we thoroughly covered important domains. We also applied various filtering methods to refine the data and uphold high-quality standards. These methods included setting token length limits, removing refusals and poorly formatted responses, eliminating incomplete conversations, and prioritizing outputs from the best models. This careful filtering was applied to both curated and domain-specific instructions, resulting in a high-quality and diverse Hermes 3 dataset. The final dataset consists of about 390 million tokens, with 270 million being output tokens that help optimize our model's performance, while the remaining 120 million are input tokens. This well-balanced dataset has greatly enhanced our model's effectiveness. Through our comprehensive approach to data curation, generation, and filtering, we have established a strong foundation for Hermes 3, addressing a variety of domains while maintaining high quality and relevance. Next, we outline our training recipe, which includes two phases: supervised fine-tuning, SFT, and direct preference optimization, DPO. The SFT phase primarily involves standard instruct fine-tuning. We chose the Llama 3.1 herd of models, which includes 3 decoder-only transformers with sizes of 8 billion, 70 billion, and 405 billion parameters, and a context length of 131,072 tokens. We utilized the Atom W optimizer with a weight decay of 0.01 and a peak learning rate of 7 millionths, following a cosine decay schedule after a warm-up period over 4 epochs. We determined the learning rate through a hyperparameter sweep, training the 8 billion models to completion and evaluating them on the GPT-4 all benchmarks. For each data sample, we set the target labels to a special ignore value for all tokens in the instruction and tool output sections, focusing the model's learning on instruction responses and tool usage. We packed multiple samples into a single sequence, taking advantage of Flash Attention 2's ability to handle variable sequence lengths, which improved the efficiency of SFT. We aimed for a target sequence length of 8,192 to align with Llama 3.1 feet's training context window, achieving a packing efficiency of 96%. For each model size, we selected the epoch checkpoint that performed best on a combination of public benchmarks. We trained using a modified version of the axolotl framework and tracked our experiments with weights and biases. For the 8 billion and 70 billion models, we used 6 HGX nodes connected with Quantum 2 InfiniBand and PyTorch FSDP for distributed training. The 405 billion model required special attention due to its size. After several trials, we found that the minimum system configuration to avoid out-of-memory errors was 7 HGX nodes with CPU parameter offloading, which slowed down training. For our final run, we used 16 HGX nodes, resulting in an effective batch size of 128. We lowered the learning rate for the 405 billion model to 3.5 millionths, which was half of what we used for the smaller models. We believe that using higher dimensional parallelism will be necessary for future training runs of the 405 billion model to manage the large number of GPUs required. Section Summary. In this section, we describe the creation of the Hermes 3 dataset, which includes approximately 390 million tokens from diverse, high-quality instruction data, carefully curated and filtered to enhance model performance across various domains. We also outline our training process, which involves a supervised fine-tuning phase using Llama 3.1 models and a direct preference optimization phase, ensuring efficient training through advanced techniques and careful hyperparameter selection. Section DPO. In this section, we apply DPO, which allows us to train a LoRa adapter instead of tuning the entire model. This approach helps us avoid the need to keep both a reference model and a trained model in GPU memory, which is crucial for larger models. We set the LoRa hyperparameters with a rank of 32, an alpha of 16, and a dropout rate of 0.05 for all linear layers. We utilize the RMS prop optimizer with a peak learning rate of 3 × 10⁻⁻⁶, following a linear decay after 9 warm-up steps. Additionally, we implement instruct-tuned with an alpha of 5. Overall, DPO showed a moderate positive effect on our benchmarks for the 8B model, as shown in the table. We also present the reward margins, which represent the difference between the reward scores of selected and rejected samples, in the figure. For larger models, DPO only offered minimal performance improvements, so we decided to stick with the SFT phase checkpoints. For our final evaluations on downstream tasks, we combined evaluations from our previous section with those from the OpenLLM leaderboard, including BBH, Math, GPQA, Musser, MMLU, and MMLU Pro. For the 405B models, we conducted evaluations using FP8 quantization. We employed the LLM compressor library for VLLM to perform round to nearest weight quantization with channel-wise activations and per token scales.